You've seen photographs of the Milky Way 1,000 times, that gorgeous band of light stretching across a dark sky, or those sweeping artistic renderings of a glowing spiral with our sun marked somewhere along one of its arms. Every single one of those images is fake, not fraudulent, not intentionally misleading, but not a photograph either. Nobody has ever taken a picture of the Milky Way from the outside because no human-made object has ever left it or ever will, using any technology we currently possess. Every image you've ever seen of our galaxy's actual shape from the outside looking in is an illustration, an artist's impression, a composite built from data, math, and educated guesswork, not a camera pointed at the real thing. Here's the part that should genuinely unsettle you. We can photograph galaxies millions, even billions, of light years away in exquisite, unambiguous detail. And yet the one galaxy we actually live inside of, the one we should know better than any other object in the universe, remains something we have never actually seen, and quite possibly never will. Tonight, we're going to find out exactly why that is. And the answer reveals something almost poetic about the limits of trying to understand something enormous while trapped hopelessly inside it. Let's start with the most basic problem, because it's almost embarrassingly simple once you actually think it through. To photograph an object, you generally need some distance from it. Stand too close to a mountain, and you can't capture its full shape in a single frame. You need to back away, gain perspective, see the whole structure at once. That's exactly the position we're in with our own galaxy. Except the scale involved makes backing away essentially meaningless as a concept. The Milky Way is roughly 100,000 light-years across. Our solar system sits embedded within it, roughly 26,000 light-years from the galactic center, tucked inside one of the galaxy's spiral arms. To capture a genuine photograph of the entire galaxy's shape from the outside, you'd need to travel far enough away, perpendicular to the galactic disk, to see the whole structure at once, likely tens of thousands of light-years away, at an absolute minimum, just to get a meaningfully complete view. For context on how impossible that actually is, humanity's most distant spacecraft, Voyager 1, launched in 1977, has spent nearly 50 years traveling outward at roughly 17 kilometers per second, and has covered a little over 24 billion kilometers. That sounds impressive, until you realize it's a little under one light day. Not one light year, one light day. To reach a distance even remotely useful for photographing our galaxy from outside, at Voyager's current speed, would take longer than the current age of the universe, repeated many times over. We are not simply far from being able to see our galaxy from outside. We are so fundamentally embedded within it that the entire concept of stepping back and taking a picture doesn't apply to any timescale relevant to human civilization, human technology, or arguably human existence at all. So if leaving isn't an option, how do we know anything about the Milky Way's actual shape? The answer involves nearly 2 centuries of astronomers essentially playing detective, using indirect evidence to reconstruct a picture none of them could ever directly confirm. Let's talk about the second major problem. Because even setting aside the impossibility of physically leaving, there's an obstacle sitting directly in our line of sight, and it makes seeing our own galaxy's structure difficult even in the limited ways available to us. Our galaxy's disk isn't just full of stars. It's also thick with gas and interstellar dust, microscopic particles of carbon, silicates, and other material scattered throughout the galactic plane, left over from the deaths of previous generations of stars. And that dust does something genuinely inconvenient for anyone trying to study the galaxy's structure using visible light. It absorbs and scatters it, dimming and obscuring anything sitting behind it, especially toward the crowded, dust-choked direction of the galactic center. Looking directly toward the heart of the Milky Way, from our position roughly 2/3 of the way out toward the disk's edge, means peering through roughly 26,000 light-years of stars, gas, and dust. For most of the history of astronomy, that dust made the galactic center essentially invisible in ordinary visible light. Astronomers knew, based on indirect evidence, that something significant had to be there. They simply couldn't see it directly because the very stuff of the galaxy itself was blocking the view. It's a strange, almost cruel irony. The one thing standing most directly between us and understanding our galaxy's core structure isn't distance or a lack of technology. It's the galaxy itself, physically obstructing our own view of its most important region, using the very same material that makes up the stars and planets within it. This obstacle wasn't seriously overcome until astronomers began observing in wavelengths beyond visible light, starting in the mid-20th century. Radio waves and infrared light pass through interstellar dust far more easily than visible light does, essentially seeing through the haze that had blocked earlier generations of astronomers. When radio astronomy matured in the 1950s and 60s, followed by increasingly sophisticated infrared observation in the decades after, astronomers finally began tracing structures that had been completely hidden before, including, eventually, strong evidence for a supermassive black hole sitting at the galaxy's exact center, a region now known as Sagittarius A. But even with these newer tools cutting through the dust, we still weren't seeing the galaxy's shape directly. We were mapping gas clouds, tracking radio emissions, tracing the motion of stars, building an increasingly detailed picture, piece by piece, without ever actually capturing the whole structure in a single image the way we can with other, more distant galaxies. Let's talk about how astronomers actually piece together what they believe our galaxy looks like, because the method itself is a genuinely remarkable feat of scientific reconstruction, built almost entirely without ever seeing the final result directly. One of the most important techniques involves mapping hydrogen gas, which fills much of the space between stars throughout the galactic disk. Hydrogen atoms emit a very specific, well-understood radio signal at a wavelength of 21 centimeters that radio telescopes can detect even through thick interstellar dust. By carefully measuring the velocity of this hydrogen gas at different points across the sky, using a phenomenon called the Doppler effect, the same basic principle that causes an ambulance siren to change pitch as it passes you, astronomers could work out how fast different clouds of gas were moving relative to us, and use that information, combined with our understanding of how galaxies rotate, to estimate their actual distance and position within the galactic disk. This technique, refined over decades starting in the 1950s, allowed astronomers to trace the rough outline of the Milky Way's spiral structure for the first time, entirely through radio observations of gas motion without ever directly seeing a single spiral arm with their own eyes. It was less like taking a photograph and more like reconstructing the layout of an entire house by listening carefully to echoes bouncing through its hallways, then mathematically working backward to figure out where the walls had to be. For decades, this indirect method produced a picture of a galaxy with 4 major spiral arms, and that 4-armed model became the standard, widely taught depiction of the Milky Way for much of the late 20th century. It appeared in textbooks. It appeared in planetarium shows. It became, in the public imagination, simply what our galaxy looked like. Here's the detail that should genuinely surprise you. That widely taught, seemingly settled model wasn't fully confirmed. It was the best available reconstruction, built from limited data, using methods that carried real, significant uncertainty. And starting in the 2000s, as infrared surveys using space telescopes like NASA's Spitzer Space Telescope provided sharper, more detailed data, that confident 4-armed picture began to genuinely change. Spitzer's infrared observations, capable of tracing the distribution of older, redder stars throughout the galactic disk with considerably more precision than earlier radio-based methods, suggested something different. That the Milky Way might actually have only 2 major, prominent spiral arms, with additional smaller, less prominent arm segments and spurs branching off between them, rather than 4 equally significant arms as previously assumed. This wasn't a minor footnote update. It represented a genuinely significant revision to how our own galaxy is depicted, arriving well within living memory, not in some distant, primitive era of astronomy. Many people alive today learned the 4-arm model in school, only for the scientific consensus to shift meaningfully during their own lifetimes. And even now, the picture isn't fully settled. Different surveys, using different tracers, whether young hot stars, older cooler stars, or hydrogen gas velocity data, continue to produce meaningfully different pictures of exactly how many spiral arms our galaxy has, and precisely how they're arranged relative to each other. This remains an active, ongoing area of research, not a closed case sitting comfortably in an old textbook. Think about what that actually means. We have detailed, unambiguous photographs of other spiral galaxies millions of light years away, showing their arm structure with total visual clarity, and the precise shape of our own galactic home, the one we're sitting inside of right now, remains something astronomers are still actively debating, using indirect evidence pieced together from radio waves, infrared light, and the careful mathematical reconstruction of things we can never directly confirm by simply looking. Let's talk about the tool that's finally starting to change this picture in a genuinely meaningful way, because it represents the closest thing we have to actually mapping our galaxy from the inside out, star by individual star. In 2013, the European Space Agency launched Gaia, a spacecraft with an extraordinarily ambitious mission: precisely measure the position, distance, and motion of over 1 billion individual stars within our galaxy, constructing the most detailed three-dimensional map of the Milky Way ever attempted. Gaia doesn't photograph the galaxy's overall shape directly, because it can't, for the same fundamental reasons no spacecraft can. Instead, it does something almost more remarkable. It measures the precise position of over 1 billion stars, one at a time, and lets astronomers assemble those individual data points into a genuine three-dimensional structural map built entirely from the inside. Gaia accomplishes this using a technique called parallax, tracking the tiny, almost imperceptible shift in a star's apparent position as Earth orbits the Sun, observing that star from two slightly different angles roughly 6 months apart. It's the same basic principle as holding your finger up and alternately closing one eye, then the other, watching your finger appear to shift against a distant background. Applied with extraordinary precision across more than 1 billion individual stars, this method has allowed astronomers to finally start resolving debates about our galaxy's true structure that had persisted unresolved for decades. Gaia's data, released in stages throughout the 2010s and 2020s, has already revealed genuinely new features of our galaxy that nobody had confidently mapped before. We've discovered that the Milky Way's disk isn't perfectly flat, the way it's traditionally illustrated in every simplified diagram, but is actually gently warped and twisted at its outer edges, curving up and down like a slightly bent vinyl record, likely due to gravitational interactions with smaller satellite galaxies drifting nearby. We've traced ancient stellar streams, the shredded remnants of smaller galaxies our own Milky Way consumed and absorbed billions of years ago. Their stars still carrying the gravitational fingerprint of that ancient collision, faintly visible in their motion even now. This is, quite literally, some of the most current astronomical research happening right now, in real time, using data still being analyzed by scientists actively working to understand it. We are, in a very real sense, still in the middle of drawing our own galaxy's map, using the most sophisticated tools ever built for the job, and still regularly discovering that previous assumptions, some of them decades old, need meaningful revision. Let's sit with the strangeness of that for a moment, because there's something genuinely humbling buried in it. Humanity has photographed the surface of Pluto, a dwarf planet billions of kilometers away, in remarkable detail. We've captured images of galaxies so distant their light left them over 13 billion years ago, before our own sun even existed. We've photographed the glowing silhouette of a supermassive black hole, 100 million light years from Earth. And yet, the actual, true shape of our own galaxy, the spiral arms we live within, the warped edges of our own disk, the precise structure of the very thing that has determined the location of our sun, our planet, and every living thing that has ever existed remains something we've never directly seen, and something we're still actively working to fully understand. It's worth being honest about exactly why this asymmetry exists, because it isn't really a contradiction, once you think it through carefully. Distant galaxies, however far away, are enormous, self-contained objects, radiating with the combined light of billions of stars, and crucially, we get to view them from a genuine, useful distance, allowing their overall shape to be captured cleanly in a single frame. Our own galaxy offers no such convenience. We're not viewing it from outside, at a useful distance. We're buried directly inside its structure, embedded in one of its spiral arms, looking outward and sideways through the very dust and gas that make up the object we're trying to study, with no possible vantage point that would ever let us simply step back and see the whole thing at once. In other words, the universe hasn't hidden its most distant, most spectacular structures from us nearly as effectively as it's hidden the one structure we happen to actually live inside of. Let's talk about what this means for the future of this particular mystery, because unlike some of the deepest unresolved questions in astronomy, this one has a genuinely encouraging trajectory, even if a complete, definitive answer remains out of reach. Every new data release from Gaia continues refining our picture of the galaxy's true structure, adding millions of additional stars to an increasingly precise three-dimensional map built entirely from painstaking measurement rather than direct observation. Future infrared and radio surveys, using increasingly sensitive instruments specifically designed to trace fainter, more distant structures through the galaxy's obscuring dust, continue pushing that picture toward greater and greater confidence. It's entirely plausible that within the coming decades, astronomers will finally reach a broad, well-supported consensus on exactly how many spiral arms our galaxy truly has, and precisely how they're arranged, resolving a debate that has technically persisted since the concept of a spiral Milky Way was first seriously proposed. But here's the detail worth sitting with as we close this out. Even if that consensus arrives, even if astronomers eventually agree, with total confidence, on the Milky Way's precise structure down to the finest detail, it will still be a reconstruction. A meticulously built, scientifically rigorous, mathematically sound reconstruction, assembled from billions of individual data points gathered by spacecraft, radio telescopes, and infrared instruments over the course of more than a century of dedicated work. It will never be a photograph, because unless something fundamental changes about the laws of physics governing how fast we can travel through space, no human being and no human-made instrument will ever leave the Milky Way far enough behind to simply turn around and take one. So here's the truth we're left with tonight. We have never seen our own galaxy, not once, not directly, not the way we've seen countless other galaxies scattered across the observable universe in stunning, unambiguous photographic detail. Every image you've ever encountered of the Milky Way's shape is an informed reconstruction built from radio waves, infrared light, the careful tracking of hydrogen gas, and now, the extraordinarily precise motion of over 1 billion individual stars, each one measured, cataloged, and mathematically assembled into a picture none of us will ever get to verify with our own eyes. We live inside a spiral we've never seen the shape of. We orbit a galactic center we spent most of history unable to even look at directly, hidden behind our own galaxy's dust. And we're still, right now, actively revising basic details about the very structure surrounding us, using tools and techniques that would have seemed like genuine magic to the astronomers who first proposed, over a century ago, that we might be living inside a spiral at all. Maybe that's the most fitting mystery of all to end on. Not a black hole light years away, not a signal from another star system, just the simple, quietly humbling fact that the one home we've always had, the galaxy cradling our sun, our planet, and everything we've ever known, remains something we understand entirely through inference, and have never once actually seen.